Hello everyone, you're welcome to this video. I remain your tutor Mr. Life Changer, and here I'm going to be showing you how to solve capacitors in series and capacitors in parallel. That's what this video is all about. Okay, so capacitors in series are placed this way. Okay, that is, I'm using three capacitors. These are three capacitors. I can call them C1, C2 and C3. Then for capacitors in parallel, this is for series connection. Then for parallel connection, we could have something like this, um, like this and like this. Okay, so these three are in parallel. Well, you could connect them to a voltage source like this. The same thing here, I can connect them to a voltage source. Okay, remember, okay, I can call this C1 here, C2 here, C3 here. Now I wrote this side by side to help us in the comparison between capacitors in series and capacitors in parallel. The first thing I like to mention is that capacitors in series involves capacitors that are arranged in series have the same charge. They store the same amount of charge. So they store the same amount of charge. So that means the charge supplied, this supplies current and or charge. The charge stored here is equal to the charge stored here, equal to the charge stored here, but they have different potential difference. So the potential difference is different because they are in series. Anytime you see a series connection, potential difference is always different. So I can say the potential difference on this one, we can call that V1. For this one here, we can call this V2. Okay, then for this here, we can call this V3. Okay, that's the potential difference. I don't need to draw this. I could just write V1, V2, V3. What matters is that we know that the potential difference is different. So that is it for series connection. But when we are dealing with parallel connection have different charges. As long as they are in parallel, the charge stored across them is different. For example, the charge stored here now is going to be Q1. The charge stored here is Q2. The charge stored here is Q3, But the potential difference, this is V. Let me call this V. The potential difference is the same. Potential difference, okay, I should say same potential difference. Okay, so is same. Okay, so this is what you should know about capacitors in series and capacitors in parallel. For capacitors in series, they store the same amount of charge, but different potential difference. But for capacitors in parallel, they store different charges but the same potential difference. Don't forget this. And this is one thing that is, will I say, common between these capacitors and resistors. Okay, is the same condition. Now, coming back to this, since we have different voltages stored across them, that means the total voltage is going to be V1 plus V2 plus V3, because we have V1, V2, V3 making up the total voltage. Now remember that the capacitance of a capacitor is the charge divided by the voltage. That's the definition. Capacitance is charge over voltage. Now since we have different voltages here, I can make voltage subject of formula. I can say V is equal to Q over C. Okay, so that means in this case now, this V I can replace it with Q over C, right? V1 should be Q over C1, V2 should be Q over C2, V3 should be Q over C3. Remember, it remains Q because Q is common, right? Q is the same for all of them. So if you notice, I can divide through by Q. If I do that, I'm going to have 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. So this is how you deal with capacitors in series, no matter how long. 1 over this, 1 over this, 1 over this. Okay, don't forget this. Okay, and but if they are in parallel, they store different charges. The total charge stored by them, I can write it as Q1. Q is Q1 plus Q2 plus Q3. Now, but if your capacitance is Q over V, it means that Q is going to be equal to CV if you cross multiply. So I can replace it. Instead of Q, I'll put CV. Q1 should be C1V. Q2 should be C2V. Q3 should be C3V. I don't need to say V1, V2, V3 since the potential difference is the same as long as they're in parallel. So since they're the same, I can divide through by the potential difference. I'm going to have C equal to C1 plus C2 plus C3. And you see, and that is that. So this is how you deal with capacitors in parallel, and this is how you deal with capacitors in series. Okay, I like to always state this. Now let us see some examples. Let's say you have two capacitors in series. Okay, let me make them three. 1, 2, 3, like this. Okay, let's say this is 2 microfarad, this is 3 microfarad, and this is 4 microfarad, and I am asked to find the total capacitance here. Okay, so in this case now I'm going to say 1 over C, since they are in series, is equal to 1 over 2 plus 1 over 3 plus 1 over 4. That's what to do here. Okay, and the LCM is 12. So 12 divided 2 is 6, 6 times 1 is 6. 12 divided 3 is 4, 4 times 1 is 4. 12 divided 4 is 3, 3 times 1 is 3. So 1 over C is equal to 6 plus 4 is 10 plus this is 13 over 12. And so you have that C is equal to 12 over 13 if you invert it. Okay, now, but I like to say this. I don't know if this is the right time to say this, or this formula you can reduce it to C1 C2 over C1 plus C2. That's the total capacitance if you have only two capacitors. Okay, you can just reduce it to this. Then if you have three capacitors, you can say C1 C2 C3 all over C1 C2 plus C1 C3 plus C2 C3 if you have three capacitors. Okay, you can just, for me it is quite faster, but if it is a theory question, then you should use this, but for me this is quite faster. So if I apply this here, it means it's going to be 2 times 3 times 4 over 2 times 3 plus 2 times 4 plus 3 times 4. You see, so 2 times 3 is 6, 6 times 4 is 24 over 2 times 3 is 6 plus 2 times 4 is 8 plus 3 times 4 is 12. So that will now be 12 over 14 plus this 14 plus 12, that is 28. 14, right? This is 14 plus 12, that's 26, sorry. So 2 here is 6 and 2 here is 13. Am I okay? This is 24. So 2 in 24 is 12. 2 in 26 is 13. So you have 12 over 13, which is exactly the same answer that I have here. Okay, so this is how you deal with capacitors in series. Please don't forget that. Now, in parallel, let's say you have something like this. It doesn't matter how many you have. I have another one here and I have another one here, and they are all connected to a voltage. Let's say this is 2 microfarad, this is 7 microfarad, this is 1 microfarad, and I'm asked to find the total capacitance since it is in parallel. In this case now, my total capacitance, since they are in parallel, it will just be 2 plus 7 plus 1. As easy as that. You don't need to break your head around it. So this is going to be 9 plus 1, which is 10. So the answer is 10 microfarad. Makes a lot of sense, right? Okay. Now we could also have cases. Let me refresh my screen. This is beautiful. Okay, very good. Now we could also have cases where something like this. Let's say I have something like this. This is this, and I'm asked to find the equivalent capacitance for this. Let's say we have this, and this. Let's say this is 2 microfarad, this is 3 microfarad, this is 6 microfarad, and this is 4 microfarad, and we are asked to find the total capacitance. Okay, Now this is what I do whether I'm dealing with capacitors or resistors. Whenever I see something like this, the parallel connection, I take them as one, okay, just one. So I will call them C1. C1 represents all this combination, and why this combination, I'll call it also C2. C2 represents the whole of the combination. Okay, so C1 is parallel to series to C2. This parallel combination is in series with this parallel combination. That's what this means. So the first one is C1. To find C1, these two are in parallel, so it means 2 plus 3, which is equal to 5 microfarad. So that is it. That's because they are in parallel. Now for C2, C2 here is going to be 4 plus 6, which is 10 microfarad. Can you see that? So if I want to find the total capacitor, since C1 is in series with C2, it's going to be C1 C2 all over C1 plus C2. You know, the formula I gave you earlier, it makes me get the answer fast. Okay, so your C1 is 5, then this is 10 all over 5 plus 10. So that will be 50 over 15. And this is going to be 10 over 3 microfarad. So that's the answer to this question. Can you see that? Okay, very, 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 very interesting. And so on and so forth. Okay, so that is it for this one. Then now we can also answer some questions as regards this. Let's assume we have a circuit like this. I have this, let's say this is 2 microfarad, and I have this is let's say 4 microfarad, and this is, let's say let me call this 6 microfarad, and they are all connected to a voltage source, and let's say the voltage source is 20 volts. And now we are asked to find some things, like for example, I find the total charge stored. Okay, so then I let's say find, okay, the voltage across the 2 microfarad capacitor. Okay, that can be a question. Then let me add a third one here. Let's say we're asked to find the charge stored in the 4 microfarad capacitor. 4 microfarad capacitor. Okay, so we have this. We can actually answer as many questions as possible, but let's just narrow it to this one. Now, so we have this circuit here, and the first question we asked to find is to find the total charge stored. Of course, in order to find the total charge stored, I must find the total capacitance. And just like I told you, this guy now is in series with this parallel combination. So for this, I can call this guy C1. This parallel combination altogether, I can call it C2. I group them as one. It's easier, okay, for me. Now, and so from there, let me separate this. That means my C1 is 2 microfarad, and my C2 is that parallel combination. And since they're in parallel, it is 6 plus 4, which is equal to 10 microfarad. You see that? So 10 microfarad for C2. Then since they are in series, the total capacitance now will be 2 times 10 all over 2 plus 10, which is 20 over 12. If you divide, this is going to give us 5 over 4 is 3. So 5 over 3 microfarad, or maybe 1.67 microfarad. Okay, that's it for the total capacitance. So now I can find the total charge, because total charge is total capacitance times total voltage, Q equal to CV. So the total capacitance is 5 over 13, or let's say 1.67 microfarad, then multiply by the voltage here is 20. And so if I multiply this by 20, it is definitely going to give me 33.4 microfarad, I guess. Yeah, I believe this is correct, 33.4 microfarad. So the total charge stored is 33.4 microfarad. Now, but I like to say something here, that This charge is the charge supplied by this. So, and that's the same charge here. The total charge is the same charge here, Q. Okay, and and it is the same charge in this parallel combination, but different for these two. I have found the first one, which is the total charge stored. The next one says the voltage across the 2 microfarad capacitor. Now, you know, the voltage, because they are in series, they have different voltage. I already mentioned that earlier. Let's say the voltage across this is V1 and the voltage across this is V2. Okay, so I can find V1 and I can find V2. So I can say that V1 is equal to Q over C1. Remember our formula. You know, voltage is simply charge over this. So your Q is still 33.4 microfarad. Then divided by C1. The C1 here is 2 microfarad. Sorry, this should be microcoulomb. The unit for charge is microcoulomb. Sorry for that. So C1 is 2 microcoulomb. So micro cancels micro. 33.4 divided by 2 is going to give me 16.7. So this is 16.7 volts. Now, since it is 16.7 volts, I have answered the second question, but I like to say this, that if I know V1, I can easily find V2, because V2 now is going to be equal to 20 minus V1. Remember that V1 plus V2 must be equal to this 20, must be equal to the total. So I can just say this is 20 minus 16.7, and that is going to give us 3.3 volts. Okay, 3.3 volts is the voltage V2. Another way you can find V2, you can simply say V2 is equal to Q over C2. Your Q is 33.4 microcoulombs all over C2. C2 is the combination, which is 10. I think we've done that before. Where is it? Yeah. C2 is 6 plus 4, which is 10. So I can come here now and say 10, and it's going to give me 3.34 volts, 10 microfarad. So you can see it's the same thing. So, but I'm going to work with this one, 3.3. Okay, so why I need that is because of the third question. It says the charge stored in the 4 microfarad capacitor. The charge stored in the 4 microfarad capacitor. Now, this 4 microfarad capacitor, the charge stored, remember charge is supposed to be CV, right? But this CV now, that Q is CV, so the capacitance is 4 microfarad times the voltage. The voltage is V2, which is across the both of them, which is 3.3. And so if I multiply this now, I'm going to get 13.2 microcoulomb as the answer to that question. This is very, very interesting. You know, I believe that you're getting a lot from this. Okay, so that's bring us to the end of this particular video. Okay, I'll be posting another one on the energy stored in a capacitor. Okay, thank you very much.